Okay. Welcome to the class. It's we are continuing the counting stuff from chapter 10. And the first thing that we left off last time is counting permutation. So here's a notion. It's called R permutation. It's a R permutation. It's a sequence of R items in a set with no repetitions. So let's take the set of the first 9 letters, A, B, C, D, E, F, G, H, I. And here is 4 permutations. So in the case of R equal 4, it's a sequence GABE of elements in the set without repetitions. Now, if I take the same elements but permute them, that's a different R permutation. So in other words, R permutation is a sequence, not a set. We'll talk about like how do you what if you take a subset, right? So that was what was, if this is not ordered, then this would be simply an R element subset of S. An R permutation is a R element subset and also with an ordering on the elements. To say that it has no repetitions means that it has to be an R element subset. So I cannot take the same element twice. Sequence would make sense if it had G, 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 right? So it would still be a sequence of 4 elements, they're all equal. But a form permutation, every element in the sequence is different. So a question, how many ways are there to pick an R permutation from an N element set? And here is how to count. Well, there's N choices of the first element, N minus 1 of the second, right? Because once you chose the first element, the second is anything except this one, because R permutation is supposed to have no repeats. Once you chose the first 2, the number of choices for the third one is N minus 2, etc. until you chose all R of them. So the last one will have this many choices, right? So this is the first, second, third, and Rth. And if you look at this, it's a product of sequential integers down from N to, there's R integers, right? Down from N. This is the same if you took an N factorial and divided divided out all the products that are missing here, which is N minus R and smaller. So you divide by N minus R factorial. And there is a symbol we use for this. It's the number of permutations in a set of N of length R. That's and it's equal to this arithmetically. So okay, here is an example of use. So let's say you have 20 computers and you have 4 tasks. So how many ways are there to assign these tasks to computers if there is no restrictions on, like, one computer can do all 4 tasks? Okay, well, so there is 20 choices for the first task, 20 choices for the second, etc., right? Because if the same computer can do the second task, then the number of choices for the second task is the same as for the first task. So it's just 20 to the 4th, because it's just a product rule, right? So for example, you can think of this as another way to think of this is the number of 4-digit strings in an alphabet of 20, because you have 4 tasks. and the first character in the task string corresponds to the index of the computer, right? And if there's 20 characters in the alphabet, then the single character tells you which computer it is. And for the second task, it's independently chosen from the same alphabet. So the choice of these is like a choice of 4 strings of length 4 in an alphabet with 20 characters, which is 20 to the 4th. But what if you had a constraint that a single computer can do only one task? So now, when I didn't notice that my animation got messed up. Sorry here. I'm not sure why, but it got messed up. And yeah. All right. So if you have a product rule, right? 20 times 19 times 18 times 17. So it is a 4 permutation in a 20 set, 20 set of size 20. Right. Why? Yeah. You have a set of 20 computers, and you take any 4 of them to run your tasks, and the order matters, because the first of the computers you take is for first task, second for the second, third for the third. So if you took the same set of computers but reversed the way the tasks are assigned, that's a different assignment of tasks to computers. So the number of possible assignments is exactly the number of 4 permutations, 4 computers taken and ordered in a 20 computer set. And that is also, so if you think of this as forming a 4 long string in an alphabet whose members are computers, so there's 20 characters in an alphabet, that's like taking a 4-character string with no repetitions. That's it, right? So if you take without this constraint, you have 20 to the 4th strings you can take, you can form, and here you have less. It's 20 factorial over 16 factorial. It's less, right? Because you can see that these numbers are strictly smaller than these ones, right? So this is a messed up, you know what? I think that because I clearly did something so that the animations are messed up, this way I can basically do you see my my presentation here? Okay, so I'll fix these slides, but I'll just not sure what happened. So okay, another case. You have 3 kids, Larry, Curly, and Mo, and they select prizes from a bin with 30 different prizes. Okay, in how many ways can they select them? So what is an outcome here? It's a selection of 3 element sequence, because it's of prizes from a set of 30 prizes. It's a sequence because it's important which of the, you take 3 prizes and then you order them. First one goes to Larry, second to Curly, third to Mo. It's arbitrary order. They are all equivalent, right? So it will be a 30 permutation in a 30 element set. Now, so let's say you have 33 prizes in a class of 100 students. How many ways are there to, I don't know, I'm not really sure what has happened at all, like why suddenly stuff doesn't show. How many ways are there to distribute the prizes if there is no restriction on how many prizes a single student can get? Okay, so So an outcome is a 3-element sequence, 3 students, right? It's a sequence, not a set, because the first is the first prize, the second is the second prize, etc. So it's three characters, and there can be repeats. The alphabet has 100 members, 100 students. How many strings of length 3 in an alphabet of 100? There are. It's 100 to the third. But if now no student can get the same prize, okay, then it becomes a 3 permutation, right? It's a string with no repeats in the characters. But there's also a string of length 3, and it's a string from the same alphabet. Students, 100 students.
Professor, did you skip 99 there?
Did I? Yes, I did. Thank you. Okay. Yeah, that's yes. Sorry. Thank you. Okay. So this gives us even okay. So more fundamental in some sense concept is a permutation. It's an ordering on the whole set, right? And a permutation is a n permutation. So I take all elements in the set and I order them. And so the number of such orderings is n factorial, right? Because I have to take the first n choices, second n minus 1 choices, third n minus 2, etc. And it goes all the way. So it's just n factorial. It's a case of note if you take this formula and instantiate with r equal n, because you take all of them, then this becomes n minus n. So it's a 0. 0 factorial is a 1. So it's simply n factorial, right? Okay. Okay, so if I say how many orderings there are on 5 letters, you say 5 factorial. Now, let's say I say number of orderings, permutations of the letters with the constraint that B and E must be next to each other. Okay, how do I do this? Okay, here is one way. You can try to do some other way, but this is a fast one. Think of B and E as conjoined. So it becomes a letter. It becomes a character. So now it's basically you're doing permutations over a set that has 4 elements. A, this BE conjoined, C and D, but you need to also remember about this possibility, right? You can conjoin them in the other direction. These permutations are distinct, right? Because it's a different set, it's a different character. So you cannot get the same order. So it is a union rule when, right? Because you basically do a top level split. Is B in front of E or E in front of B? That's a partitions of the space. And then you count each of them separately as just a 4 permutation. So it's a 4 factorial twice. Okay. Okay, so the how many where B comes immediately before E? Okay, we already know that it's 4 factorial. And now look at something. At something, an application of a 2-to-1 rule. Let's say that I want to count all permutations in the set with a constraint, not that B and E are next to each other, but that B is somewhere before E. And now how I do it? Okay, well, maybe I can enumerate all possible ways that B and E can stand in position to each other, but it's going to be onerous. There's going to be many possibilities. Well, what's a shortcut? Well, maybe a eureka moment will occur if you see that you can split, that this is symmetric. In all permutations, either B comes in front of E or E comes in front of B. There's no possibilities, other possibilities. They cannot be on the same position. And is there any reason to believe that the number of permutations where E comes before B and the number of permutations where B comes in front of E are different? It seems completely symmetric. Indeed, we can show the symmetry by a 2-to-1 rule between all permutations and permutations where B is in front of E. What's this 2-to-1 rule that will map all permutations to this restricted set? Here is the function. Take a permutation. See, is B in front of E already? Then do nothing to it. Just output that permutation. But if B and E are switched, so E is in front of B, then the only thing you do with the permutation, you switch the two and output that. It is a 2-to-1 mapping. This function f didn't touch any other elements except of E and B. So if they were different to begin with, then they were different when the function output. The only thing it did was look at B and E and either keep them or switch them. So therefore, only two things can map to the same. B and E in this way or B and E in this way. They will be mapped in a correct order where B comes before E. So it's a 2-to-1 map. So therefore, now is it does it get anyone from the range? Yes, it does. Right, because in better words, it's an identity on the set of on this partition. So it's a 2-to-1 map. So therefore, just count all and divide them into 2. So these are the shoes, and these are the, I take shoes and divide them by 2 because every kid has 2 legs. And so I get the number of kids, right? But here it is a non-trivial case. It is not obvious how to count these. If you try to count them, in other way, you can also see this as a case of a 1-to-1 rule between permutations in this between two subsets of permutations where B and E are in front between. But the 1-to-1 rule is not going to be so easy to count. 2-to-1 is the way to go here. Okay. Now let's move on and count subsets. Okay, so unordered structures. So let's say we have 2 counting problems. You have a student council has 15 students, and you must select a committee that contains president, VP, treasurer, secretary. So you're taking 4 out of 15, and you giving them special functions. So the first one is going to be a president, the second VP, the third treasurer, the fourth secretary. This is the 4 permutation because the order matters in the sequence. You take 4 and you order them. But what if you just had say, okay, you have a council and now you have a committee, let's say executive committee. So the members are not ordered, they're just members of the committee. So what you select is not a sequence, but a set. And because the order of people within the committee doesn't matter. So it's a different counting problem because 2 different permutations might actually be the same set, right? Any elements of these, but permuted. So how to count that? Well, let's do some examples. So you have a 3-element set and you take a 2-element permutations. So 3 choices for the first one, A, B, C, and then once first is chosen, there's always two choices for the second element, right? What about two element subsets? Okay, so that I know how to count is 3, but is there a general formula? Well, I can get this formula by a k-1 function. Let's take 3 element subset, 3 element sets or permutations. If my set, has 5 elements, but it could have many. When I'm asking how many ways to pick 3 elements from these 5. Well, I actually already know how to count ways of choosing 3 elements in an ordered way, right? So this was n factorial divided by n minus 3 factorial. Now let's consider the following functions that will map the 3 permutations, which is what I know how to count, to 3 subsets, which is what I want to count. And the function is obvious. Take a sequence, which this is, and output just elements, a set containing all the elements in that sequence. In other words, if my permutation is blue pink green, the set will be blue pink green. But if my permutation is the same things but permuted, my set is still the same. The set I output is the same. So it's an example of a k-1 function. If I just need to find k, because I know how to count these things, and if I knew the k-1 in this function, then I would know how to count these things. I would count these, divide by k, and that's what I would get. So what's the k in here? Well, k is easy. It's the question of how, for any image, for any value that the function can output, how many pre-images are there? That's your k. So the function is, if I take 3 elements and basically I kill the order between them, which is what that function does, it's like an order eliminating function, order flattening function. Then how many things will get mapped to the same? Well, as many as there exist permutations of this set. So if the set has 3 elements, then the number of these is 3 factorial. So the k in the k-1 function is 3 factorial, which is in more generally r factorial. If you're taking an r element set, it's an r factorial between them. So let's put it together. So therefore, since this is it's a k-1 function where k is 3 factorial, the function mapping all permutations to just sets, then in order to count the green things, the sets, I take the number of red things and I divide it by 3 factorial, which is the k here. And so, so the number of subsets is the number of permutations divided by r factorial. Permutations is this symbol, p and r, but now I divide it by r factorial. So what is inside here? It's n factorial divided by n minus r factorial, but I still have to carry this out. So it's this. And it's n factorial divided by r factorial and n minus r factorial. And it has a special symbol. It's n over r in brackets. This symbol stands for, it's called combinations. It's number of r element subsets of n element set. This is the only thing the symbol stands for. And you should use no others also, like don't put a dividing line between this, because that's a big, that looks as if you just do an integer division. it's a special symbol that denotes this quantity. And we only use it for integer on integer domains. Okay, so this is the symbol is read. The number of R element subsets from a set of size n is n choose 4. That's how we read the symbol too. N choose 4. Another notation is people see. So I think the book doesn't do that, but they also write this C of nr. It's a sort of parallel notation to the permutations nr. I don't like this notation. I never use it, but some people like it. Okay, let's see how. So this is the again, n choose r is the number of R element subsets in an n element set. So let's look at, okay, how many 2 element subsets there are of 6 element set? Okay, it's 6 factorial divided by 2 factorial and n minus r, which is 4 factorial, right? So n is 6, r is 2. So you get a 4. If you numerically compute it, right, so well, you can cancel all the factorial, 4 factorial here, and you just get 5 times 6, and this part drops out, and 2 factorial is just 2. So it's this, so it's, well, I can just take, replace 6 over 2 with a 3, it's 15. Now, if I look instead at 4 element subsets of a 6 element set, then R is now 4, so it's 6 factorial divided by 4 factorial, and n minus r is 6 minus 4, so it's 2. But that's the same quantity, so I already know this is 15. And by the way, this is not coincidental, right? So you can see that if I choose 2 element sets or 4 element sets, yeah, if this value is equal to the difference between these two, then I can replace this with that, and it would make no difference. Let's look at taking a 500 element subset in a 500 element set. Okay, so it's like I take everyone. So there should be only one way. Just take everyone. There's no choices. Indeed, if you stick it in here, you get 500 factorial divided on 500 factorial would cancel out. And here is a 0 factorial, which is a 1. So the formula does give you the expected value. What if you just take 1 element subset in a 500 set? Well, so that's just like how many choices you have, 500, right? Like because it's just a singleton. So there's 500 choices. So let's see. It's a 500 factorial divided by 499 factorial. That's r. Sorry, the 499 is n minus r, right? 500 minus 1. So I get 599 factorial. It's n minus r. And the r is 1. So 1 factorial is just 1. And 500 factorial divided by 499 factorial is like everything drops out except of the last factor, which is 500. So again, that's what we expect. So here's the general rule. If you take an R element subset, if you n choose R is the same as n choose n minus R. And you can check this, right? Because n choose R is this quantity, and n choose n minus R is you replace R with n minus R. So, okay, so we do this, but look, n minus R, n and n cancel, and you get plus R here. So this quantity really comes down to this one, and this is just reordering of terms to get this, right? So it's equal. But here is a more interesting way to test this, because it corresponds to a very simple combinatorial phenomenon. we can show it by a bijection, following bijection. Take a set from which you're choosing. Let's say you're choosing R subsets. So subsets of size R. You can think of any such choice of an R subset as a choice of n minus R in the complement. And these are equivalent decisions. When I choose R elements in a set, I could equivalently choose n minus R in its complement. And this would be, it's really the same choice. I can represent the same choice in two different ways. That's this function that maps an R element set into an n minus R by taking its complement. So n choose R is the way of is the number of choosing R element subsets. N choose n minus R is the way of choosing n minus R subsets. And if I just think, replace thinking of R element subset choice into thinking instead of choosing their complements, then this becomes this problem, right? Because like whether it's a complement of something or it's just a set, that doesn't matter. So this is a case of a one-to-one function where, let's say I didn't know how to count this. I do, it's this formula, but I only knew how to count R element sets. Okay, this function allows me to map all choices of these as choices of those. And choose R is a way of choosing those, so therefore that must also be a way of choosing these, and the formula checks out. In other words, you know, from this it follows that these two must be equal without resorting to arithmetics and seeing what arithmetically these formulas resolve into. So where do you count permutations and where do you count subsets? Okay, like just an example. So you have a pianist in a competition, and you want to select 25 of them to go to the next round. Well, so the order doesn't matter. So it's 100 choose 25. You choose 25 elements out of 100. But what if you choose, let's say in the next stage, there's 25 of them, and now you actually choose first, second, third, fourth, and fifth place. So it's not 25 choose 5, which would be unordered, but it's a permutation now of 5 elements from 25 in an ordered way. Okay. Okay. So let's review where we are, right? So if we have a process that says you choose either one type or another, and these two types are not intersecting, then in other words, it's two processes that are exclusive. So it's just a disjunction of them. It's either that or that. That's where you sum rule. You count all x's and you count all possible y's and you just add them. If you have two independent processes where choices of one and choices of another, of the second one, are piled up on top of each other. In other words, as if like you choose one x from the first process and one y from the second, then it's a product rule. You multiply this the number of x's and the number of y's. Sequences, orders, they're ordered and repeats are possible. This is just cardinality of the alphabet from which you take these elements to how many elements you took. What if you have constraints that you're taking n elements from this set of alphabet A, but there's no repeats? That's a R permutation. And what if you actually, these R sequences are unordered? So they're no longer, it's a string of characters, it's a set of characters. That's the cardinality, choose R. Okay, let's use it with some examples, counting different types of strings. So how many binary strings, or how many 9-bit strings have exactly 4 ones? Well, you can count them in different ways, but here is a convenient way. Choice of such string means just choosing 4 positions among the 9 where ones would go. These positions, you have to choose 4 positions because the string has to have 4 ones. And you cannot repeat. I mean, it makes no sense to choose the same position twice. Also, the order doesn't matter. It doesn't matter in what order you take these positions. I mean, the positions are ordered. There's first, second, third, fourth. They're integers from 1 to 9. But when I take 4 of them to determine where the ones should go in a string, it doesn't matter whether I chose the last position at the beginning or at first. So it's a subset that I'm choosing of positions, of 4 positions in a set of 9 positions. This, by the way, was also, I was saying something called characteristic string of a set. We used it in the previous lectures. Well, for another example, there is a natural correspondence between subsets and bit strings. Any subset can be represented as a bit string that has a 0 if that index is not taken. So, like this, for example, string, this string represents what subset? 1 is not there because the first bit string is 0. Bit is 0. 2 is taken because this bit is 1. 3 is skipped, 4 is skipped, 5 is taken, 6 is taken, 7 skipped, 8 taken, 9 skipped. And that's the set this bit string corresponds to. Conversely, I can map the set to a bit string like this, right? It's a one-to-one correspondence, which is another, it's a formal proof that that's how you would count. So therefore, any bit string with a fixed number of ones basically means a subset that has a fixed cardinality. And that we know how to count, right? Because it's n choose the cardinality of the subset. Okay, another examples. So say you have a decimal alphabet now, and I'm asking how many strings over decimal have length 8. Okay, well, that's 10 to the 8. Now, how many of these have exactly 3 5s? Okay, maybe I can break it into 2 processes like this. First, determine the spaces where the 5s are going to go. So I'm taking a length 8 string, okay, and I have to have 3 5s in them. Okay, so let's choose the positions where the 5s would go. How many choices? It's a set of 3 positions among a set of 8 positions, right? So it's 8 choose 3. And now I set my 5s into these. And the second process is, is different. it chooses all the remaining characters, of which there are 5, without constraints, except for one constraint, which is that there are no longer 5. Because the 5s were set, the string has to have exactly 3 5s. So all the rest cannot be 5. So I just choose now from a reduced alphabet Z10 with the 5 kicked out. This is the set difference. And I choose how many are left. I took 3 positions out of 8, occupied them by 5. So there's 5 remaining positions. And repeats are okay. So there is no other constraints, right? So it's 9 to the 5. Oh, product rule, because these two processes were independent. You could literally do this. You can choose these strings like this. Tell one person, you choose the position of 5s, and tell the other person, you choose the 5 remaining digits and order them. And now, given these two choices, you can create a string. You're going to have to convince yourself that these processes will create all strings with this given constraint. That's one thing. And that they will create without collision. So there is like no 2 ways to choose the same string. But that's correct here. Yes, the positions of, there are unique positions. For any string that has this constraint, there is some positions, right? So they can be chosen here. Okay, but both are important that you get clarity. You don't overcount and you don't undercount. It's not so clear, like, how do you come up with this stuff, right? You just try, and the more examples you see, the more you will be comfortable as to, okay, I have seen some constraint like this before. How can I represent it? Is it like choosing a set, or is it like choosing a sequence? Are repetitions allowed? Can I split it into some 2 processes that are easier for me to count each one? That's the kind of stuff you will be asking yourself, and that's how you'll be moving through the space. So let's say I have I complicate it by saying these are 8-digit strings and they have exactly 3 5s, but there's 2 1s. So now I split it into 3 parts. Somebody chooses these 3 positions for where the 5s go. Somebody chooses 2 positions out of the remaining 5. And remember, positions are ordered. So I don't need to know, I just relatively, I can define 5 positions that remain after all the 5, the positions where 5s went are taken out. So it doesn't matter whether the 5s are injected, which way they are injected. It's well defined, the remaining 5 positions in an order. So somebody chooses where the 1s would go, and there's 2 places. And then the remaining digits, well, they have to now avoid both 5 and 1. So it's a reduced alphabet that now has only 8 characters. And you choose 3 elements from it. And there is no constraints, so they can repeat. Therefore, it's just unconstrained number of strings of length 3 over the alphabet, which has 8 members, 8 characters. And because these processes are independent, I multiply them. So you can arrange it differently. You can, for example, first choose the 1s. You can then choose, or maybe first choose these. It doesn't matter. It would be always the same if you count without undercounting or overcounting. You would get the same thing. And this also maps into a question of whether what I'm counting is somehow distinguishable or indistinguishable. So look at this example. Let's say I have 275 people, like students in the class, and 10 prizes that are like a A+ grade. But they're identical, like every A+ is the same. So how do I, so students are, now I ask, how many ways are there to distribute these prizes to students? Well, in this question, the prizes are identical. So how many ways are there to give A+ if you know that you have a budget of 10 A+ in the class among 275? So the prizes are identical. The people, though, are not. So the assignment of A+ to this set of students and that set of students are different assignments. So you can represent this process as choosing people, as like you have the prizes and you map them onto people. You take 10 of the people, so it's like a 10 element subset in a 275 element set, right? The choice of 10 out of 275. But what if the prizes were different? That's like let's like taking a sequence instead of taking a set, because you take 10 and now you order them because it matters which order they are taken, right? The first takes the first prize, second, and so forth. So that becomes a 10 permutation out of the 275 set. Whether or not what you in both cases you distributed some 10 objects into the 275. In both cases there couldn't be repeats, like you cannot place the same price, two prizes on the same person, and you also cannot okay, so repeats of this choosing the same element from a 275 set element set, that cannot be done. And the only difference between them was whether you were choosing distributing identical prizes or different prizes. And this translated into taking an unordered 10 element set subset versus an ordered 10 element sequence. And now, what if you had that you had the different prizes, but you remove the restriction that the same person cannot get two prizes? Well, this would be just taking any string of length 10 out of alphabet of 275 characters, because the same character, a student, can occur many times in the sequence, right? Because it's the sequence, because there's 10 different prizes. There is a missing spot in this diagram. What if you have identical prizes and you remove the constraint at most one per person? Now you can say, what sense does that make? Like a same student cannot get A+ twice as a final grade. But there is going to be problems where have the structure, where when you hash onto data structure, maybe two elements will hash into the same box. Okay, and well, okay, but identical. Well, so you will see an example of that very soon, I believe, next time. Although at first maybe it's hard to think of, like what natural problem would correspond to giving distributing identical prizes into among the group of students and allowing collisions. and how would you count, right? Like it's a natural problem. Okay, I think this is a good place to stop. Next thing, I will have many card counting applications. You can read up about playing poker in the iBooks. Okay, I'll stop recording.